In this video we're going to look at some integration techniques and kind of start mixing a little bit of substitution with non-substitution. Like this first one, this is an old kind of integral. There's nothing here that I really can't handle with just raising the power and dividing by the new power. The antiderivative would be 2/3 x cubed. We're going to evaluate at 2 and 0. If I plug in 2, I get 16/3. If I plug in 0, I get 0. So the answer is 16/3. No substitution necessary for that. Next, now this one I look at, I've got a product, right? I've got x squared multiplied by e to the x cubed. And there are a couple things I guess I look at. Besides the fact that there's a product, I look at the fact that if I made u x cubed, the derivative of that would be 3x squared. Maybe I could get rid of the x squared term through substitution. So that's what I'm going to try and do. I'm going to make u equal to x cubed. Okay, so then du is 3x squared dx. Now again, I know that at the beginning of doing substitution it's sometimes easier to rewrite with the kind of u part first. So you've got this, just changing the order of the multiplication, because of course multiplication's commutative. So x squared multiplied by e to the x cubed is the same as e to the x cubed multiplied by x squared. Well, now going back down to my du, if I divided both sides by 3, I have 1/3 du is equal to x squared dx. Well, that's exactly what I have right here. So I obviously can replace x squared dx with its equivalent, which is 1/3 du. So let me do that. I'm going to have the integral of e to the u multiplied by 1/3 du. I'm going to bring that 1/3 out front, okay, because it's just a constant multiplier, so I'll just zip that right out front. So now I just have 1/3, or e to the u du, which is pretty easy. Now I also want to redo my bounds. Okay, you'll see here the bounds used to be 1 and 3, but that was in terms of x. Well, if I plug 1 in here, 1 cubed is still 1, so the new bound, the new lower bound, is still 1. But if I take the upper bound of 3, 3 cubed is 27, so that's my new upper bound. So the antiderivative of e to the u is e to the u. And I still have a 1/3 out front. And I'm now evaluating at 27 and 1. So I have 1/3 e to the 27th minus 1/3 e to the 1st, which is just e. And this is my answer. Now you could certainly go back to x's and have it resubstitute in 1/3 e to the x cubed, and then your bounds would go back to being 1 and 3 and being in terms of x. But I think it's just as easy if you've rewritten the bounds to stay with it in terms of u. This last one, the antiderivative of 3 over x is 3 natural log x. The antiderivative of 2x is just x squared. We're evaluating at e and 1. So 3 multiplied by the natural log of e is just 3. So we have 3 plus e squared when we plug e in. Minus, well, the natural log of 1 is 0, so here we have 0 plus 1. So combining our like terms, we end up with e squared plus 2 as our solution. Alright, we want to just quickly look at some ways we can do some trig derivatives with substitution. We've not talked about the antiderivative of tangent before, and the reason was we need substitution to do it. I'm going to start by rewriting tangent, just like you did in pre-calc all the time, as sine over cosine. Well, now, if I make u cosine, then the derivative of that is negative sine Okay. And again, if it helps you see it, let me rewrite 1 over cosine multiplied by sine, like that. So now I could change the sign here, make it negative d theta, and again I can replace sine theta d theta with a negative du. So my new integral becomes 1 over u multiplied by negative du. Well, let me bring that negative out front. Okay, let me just knock that out front. So now I just have 1 over u. The antiderivative of 1 over u is the natural log of u, but I have a negative out front. Resubstitute. And there it is. Sometimes you'll see this written as the natural log of secant. That's because using your some of your rules for logs, you could bring the negative in as a power and have it be cosine theta to the negative first, which is 1 over cosine, which is secant. Okay, so this is the antiderivative of tangent. Let's do another one. This one I wanted to show you that a little bit of rewriting can maybe make this easier. Now certainly you could do this as, sine cubed over cosine cubed divided by cosine squared, which would be sine cubed over cosine to the 5th, and then you could do it very much, you could try and do some adjusting like we did before. But I think it's going to be much easier to rewrite this in a couple of steps. So tangent cubed multiplied by 1 over cosine squared. Well, 1 over cosine squared is the same as secant squared. And now it's a pretty... So if I made u equal to tangent, then du, it's the derivative of tangent, is secant squared theta d theta. I'm going to be able to replace this entire thing with just a du. So my new integral becomes, well, instead of tangent cubed is now u cubed, and du takes the spot of everything else. Okay. Now, the reason you can't make, because sometimes people will say, well, why not make u equal to the whole thing, tangent cubed? Because if you think about tangent cubed, you're going to need to use chain rule to find the derivative, and you're not going to have as nice a du for replacement. Okay, this was enough. Okay, so raising the power, dividing by the new power. Let's see. Place. There's our answer. Our last example is cosine cubed. This is sometimes referred to as the Peel method. And what that means is that we're going to peel a cosine away from cosine cubed. And the reason we're going to do that, I think, will become evident as we do the problem. I'm going to start then by peeling a cosine off. So I'm going to have cosine squared multiplied by cosine, because of course that is cosine cubed. The reason I did that is, of course, this I can't really integrate because there's no du. Now, over here, of course, it looks like I could make u equal to cosine, but du would be negative sine, so that's not what I have here. But I could replace the cosine squared with an equivalent based on a trig identity. So let me rewrite again. Instead of cosine squared, I'm going to write 1 minus sine squared. Okay, remember, 1 minus sine squared is the same as cosine squared. That's a trig identity. Well, now it's pretty easy to see that if I make u sine, du will be cosine. And look at that, I'm going to be able to replace that entire thing with just a du. So my integral becomes 1 minus u squared du. Okay, so now we do the antiderivative. Now the antiderivative of 1 is u, because remember, u is the variable. So u minus 1/3 u cubed plus c. So I substitute back in, I have sine theta minus 1/3 sine cubed theta plus c. And here is our antiderivative.